Hey everybody, this is Larry. This is day 5th of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem if it ever loads. Why is my computer so slow? I don't know. So slow for Leetcode? What is going on? Alright, today's problem is... am I lagging? Yeah, it seems okay. Today's problem is 229, majority element 2. Given an integer array of size n, we find all elements that return more than n over n over 3 times. Okay. I mean, obviously, linear time, linear space is trivial, right? We just put everything in a dictionary, and that should be fine. And then the other one is it Freud? It's someone's majority algorithm. I forget the name. But that's also that's n over 2 times, so you can kind of do the delta things, and you could do that in also O of 1, but that only do n over 2 and not n over 3. And in this particular case, I guess the 4 of n over 3 or more than 4 of n over 3, there could only be at most 2 elements, right? So maybe we just have to do some maths there. And just to kind of jump ahead a little bit, is that I'm trying to attempt to solve the follow-up, the linear time constant space, because like I said, otherwise you just put everything in a hash table or lookup table or whatever frequency table, and it's fine, right? Let me think. Because I think, I'm trying to see if I can generalize. Is it Freud's majority algorithm? I forget the majority algorithm. That's a thing, right? Or someone else? Who did it? Oh, Boiler Moore. Okay. So another famous computer scientist, but I've been mixing it up today. I think that, actually, to be honest, the majority one, I always mix it up. Maybe I always say Freud. I give Freud so much credit. But in any case, yeah, so I'm trying to generalize, try to see if I can generalize that to from n over 2 to n over 3. I don't know if I can, per se. I do have some, I think I have some ideas around it, but I have to kind of really work it out, to be honest. Because I think the O of 1 space could be a number of things, but really, like I said, you only have 2 possible answers, right? You have the number 1 answer, or like the most common element, and then the second most common element, and then maybe the third if I'm wrong by a little bit, off by wrong by and off by 1, then you have 3 majority elements, right? Yeah, I mean, I think it still should be only 2. So maybe we can definitely consider doing that, and then maybe keeping track of it, right? So, and I'm just trying to generalize Boiler more in my head anyway. The majority algorithm is just this idea of this delta, right? Because basically, the idea of I might be wrong here because I'm trying to do it from memory, is that the majority algorithm is that any number that appears that is not the majority will be -1. That and it is very. I mean, I get the idea, but it is still a little bit weird the way that it does. Like, if a number is, I mean, of course, I guess you're supposed to do one more pass at the end to kind of confirm it. So I guess that's fine. But the question now is then, is there an idea that does that here, right? So how do I check whether one number is appears 1/3 of the time or more? And we can probably do it in a number of passes, or like as long as it's a constant number of passes. But let's say, and this is me thinking off my head, so definitely you're seeing the live thing now. I have solved this before though. I don't know if I was just lazy because I don't think I have a feeling about it. But I sometimes I say that, so and then I'm just wrong. So, but okay. So how do you get 1/3, right? That means that okay. So I think my idea here now is that so to get 1/2, the Boyle-Morris algorithm is that for every one there's a matching one for every majority there's a matching minority, and if you go over it, that's fine. So for 1/3, for every one you have two elements on the minority. I wonder if that works, right? So basically, one has to cancel out two things. So if you have, I do wonder if that works. I mean, that's kind of my idea at the moment. I think that works because I think the worst case would be something like, and I'm just going to use letters for some laziness. So A B B B B B B B, right? So then my algorithm would be like +2, and then now the four of these would cancel out the A's, and then now we have B's going forward. Yeah, maybe that's fine. I'm gonna try it. YOLO, right? It sounds reasonable in the same way. But I don't know. Is that true? What if we have half? No, I guess half is fine. And then we could do the second pass much easier, right? Okay, let me try this. To be honest, the proof is tricky, so I don't know. But I don't know if it quite works, but we'll see. So yeah, so current is 0. Just say, and it could be negative number. So let's just say some numbers that's still out of range. So infinity, right? And then maybe the delta is equal to 0. I forget what they call it in the algorithm. It's been a while. And then now for each number, if x is equal to current, delta increment by, let's say +2, so then we get delta -1, else delta -1, right? But if delta is exactly 0, then current is equal to x, so then we can kind of just abuse it that way. Okay, so then now if I guess okay, so if delta is greater than 0, for sure we have a number that is more often than 1/3. But if it doesn't, does that mean it is not? That I'm unsure about. Like if delta is negative, does that mean there's no elements that appears more than n/3? I think that's the thing that I'm not quite sure. But I guess it cannot be negative actually. So, and I guess it can always be delta over 1 at the end. But that's why you do a check, right? Okay. So then, if delta is greater than 0, because I guess if delta is equal to 0, then actually by definition it cannot exist. Maybe, but maybe I'm wrong on this. I may be wrong on a lot of things. This is a really weird specific problem, right? That doesn't, I don't know that generalized into anything, so I don't know. But yeah. Yeah, so okay, so if it's greater than 0, then we have to run through, just num start count of current, right? So I don't know, C is this. If C is, let's just say we have an answer array. If C is greater than n/3, multiply 3 by on both sides, and then n start append current, right? Whew. And then now we're now we have to see if we can figure out the other one, right? I was initially gonna think like, oh, you just do the n over two algorithm for the rest, which is not quite precisely true, right? But we can definitely like remove. Like, what happens when we remove these elements? Well, if we remove these elements, like the most popular element, we still need n over 3, which is a little bit tricky. I think we could do the delta thing again and then do the math that way, but that seems a little bit, I don't know, it's just too hand wavy for me, to be honest. Okay, that's actually, what I want to do now is just actually run it for some examples first. I know that this is going to be wrong because only outputs one answer, but I also want to put in like a few more other things. That should actually return something. Even though this is 0, so I don't know. Yeah. So maybe this is wrong. Because this should definitely, like, even if I had, I think my logic is a little bit wrong here. Or there are a lot of things that are very wrong here. But like, even if I have something like this, 2 should be there. So now the order is not quite right, is it? Or like, it's order sensitive, which is, oh. Well, I guess the 1 works. But that's like a really weird way to do it. Because I think there is another invariant that I'm not considering. Because basically, if let's just say we have, yeah, I mean, I think this still should have returned a 2 if we wanted to write as the most popular item, and this definitely is not the case. So maybe we have to do something else. I don't know. Now that I think about it, to be honest. Is there a funky way to think about this problem? I was just thinking about generalizing Boiler-Moore's majority algorithm, but maybe this isn't it. Maybe that was a red herring, and I apologize for wasting 12 minutes. But, you know, we're trying to learn here. I'm trying to think whether I can binary search, is what I'm thinking right now. What does the binary search look like? You do a binary search. Well, or at least like for one of the answers, not necessarily all of them. 1, 2. No, you can binary search because let's say you have -1, -1, -1. You have 3, I don't know, some whatever, right? Then in theory you would try to do a search on this side, but that's just not how that works out, right? So I don't think that you could. What's going on? I don't know that it's as easy as a binary search. Huh. Maybe I just don't know this one. I mean, this is a very weird thing. Yeah, maybe the delta thing just doesn't work quite like that. Or maybe I just don't understand the majority algorithm enough. It's because I'm trying to think everything off my head. I'm not, you know, googling it or whatever, googling it. Or it's not yet. Hmm. Huh. I don't know how to do in constant space. Just do. I'm just thinking about like if there's a permutation thing, but I don't think so. There's no counting sort or anything like this. That's still all linear space. No, that would be funny if that was just a thing, like as a counting sort. We're like, well, okay, that's not useful. But oh man, I'm tired. How do I do this one? I thought that this would give me the most popular element. Well, I guess that's not true. It's just at least one element. I actually did not anticipate it giving me nothing for this one. I mean, it makes sense. It's just that I don't know. I just didn't think of it all the way through. Um, so now, I mean, I guess you can remove ones, and then you need four. How do you even calculate that? You use the delta trick again? Eh, I don't know. Hmm. Is there anything like with pigeonhole that I can kind of use? Um, or even probabilistic? Okay, let's try to solve the n over 2 case, right? If it exists, can we binary or break like a divide and conquer? With the n over 2 case, you could divide and conquer because the most common element. Oh, I guess that's not true. I was gonna say that the most common element is probably the most common element on the left and on the right, but I guess that's not technically true. Because it could be like the second element on the left and second element on the right, and then combined it as the number one element. But you only need to go too deep. How do we get the two most common elements without storing a frequency table? I guess that's the question. Can I just do this with three elements? Okay. Do I subtract one on each one then, if it's not? Yeah, I don't know. I guess technically this as well, because this is 4 of n over 3, which is what they want. So this is too precise, actually. I don't know that I can times 3. Maybe it should still be fine, I think. But I'm trying to think whether how to kind of quite translate this. I'm thinking maybe something like, I don't know if this generalized. I think that's the thing, right? So okay, so you have like current 1, delta 1, right? And then maybe like, if current 1 is equal to or if delta 1 is equal to 0, current 1 is equal to x. Else, if delta 2 is equal to 0, then current 2 is equal to x. Oh, well, actually, the order has to be precise, I suppose. If current 1 is equal to x, then delta 1 increment by 1. Else, if... So then now it is not nothing to do, then now 2. Set it. Else, if current 2 is equal to x, then delta 2 increment by 1. Else, I don't know, something like this maybe? I don't even know if this is quite right. But I guess, I mean, I'm trying to make sense of it. I think it makes sense in a way that, like, it matches the other thing. Because if you think about it the same way, then now... but I don't know. I think that's just really tricky to say and do, right? Right, if delta 1 is... I mean, I think we just do like C1 or count 1 is equal to num sub count, whatever. I'm a little bit lazy on this one, of course. Right? Right? And then now, if... And we could actually write this in a loop. Right? What is it? I know. Something like that, right? But this is a little bit awkward. No, but this should only happen if it is not this or this, and they're both not zeros. So I think this means that this implies everything will be positive. I think this has to be... Okay, I think I missed something here. Because you just start off at 1. Okay. Give it submit, but... Yeah, I wasn't confident about this. So that's... okay. Let's see why this is wrong. So it goes 2, and then 1... 1, 1, 3. So the 3 deletes the 2. Okay. And then when it gets 4, it should go back to 1. And what is the answer? 1? Am I just off by 1? Maybe I am a little bit... The rounding is a little bit weird. Does that fix it? Nope. Okay. Let's see. Five and 6. Okay, so the 4 4 should not delete the 1, but the 3 would. So okay, so the 2, 1, and then the 3 delete one of them, 4 doesn't, but then the 5 and the 6, so now delta 2 is equal to 0. Or when the 6 what? Maybe do I have a typo or something? Let's print everything, I think. Why is there so many things? Okay. So 2, 1, okay, that's good. Another 2, 0, 0 set. Oh, I see. So one of the ones got put it the other one. Okay, so I guess we have to move these things up a little bit, just in case. I think I just had it with the other way in the other one, and it kind of influenced my mind. This is kind of a hard problem if you haven't done it before, or if you don't really understand the Baltimore election algorithm or majority algorithm. Did it before? What did I do? I guess I did do it that way eventually. Huh. That was 3 years ago, so maybe it was just a long time. This is kind of hard to explain. I mean, this is linear time constant space. It's a little bit hard to explain, but it really is just the same idea as the Baltimore majority algorithm, which is that, the idea is kind of like pigeonhole in that the majority algorithm or the majority element will cancel out one non-majority element, and then that means that if you kind of do a counting one by one, there would be, if there exists a majority algorithm, it will have more elements than it would have leftovers because it's just the number of elements that are left. And here, we're doing x over 3, I guess you generalize it in a very awkward way. For me, it feels awkward, which is that if you have two major elements, then each of them, not considering the other, will cancel out one of the third, or the non-majority algorithms, or the minority elements. I guess that's kind of the idea, but it's still kind of tricky to come with, to be honest. And it really doesn't come up that much, but it is a classic problem, I suppose, in that because I think the way that I read this is that, back in the day, like, I don't know, like caveman days or something, right? You don't even need a concept of numbers to know what is bigger, because the way you would do it is just you would count them off one by one to kind of get to see who has more, right? So that's kind of the basis for this one as well, a little bit. But of course, it's not sufficient. So that's why I would do the count at the end, because you can imagine, you just have something like, I don't know, like 1 1 1 1 1, and then 2 2 2 2 2, so they cancel out, and then 3 3 3 3 3, and then now, or even just like 3 4 5 6 7 8 or whatever it is, right? Then now you would have the last element would have one extra element, but that obviously is not a majority. That's why you have to do a count. But yeah, linear time, constant space. That's all I have for this one. I'm really exhausted on this one. Let me know what you think. I don't know. I don't know how I feel about this one. So yeah, stay good, stay healthy, take good mental health. I'll see y'all later and take care. Bye bye.